Time only moves forward, and this simple fact hides a cosmic mystery. We live inside a one-way street of seconds and years, a flow so constant we rarely question its engine. This video will reveal the true origin of time's arrow, a discovery that reshapes your understanding of reality itself. Why did our universe begin with a configuration that forces time to march ahead? And what does the inevitable heat-death of everything mean for our existence? By the end, you will know exactly why the past is locked away and the future remains forever out of reach. What single moment from your own timeline would you most want to revisit if you could? The fundamental rules of the cosmos present us with a profound contradiction. If you could peer into the mathematics describing reality at the level of atoms and forces, you would find something astonishing. The equations crafted by minds like Isaac Newton and even the stranger rules of quantum mechanics do not care which way time flows. They are perfectly symmetrical. A planet orbiting a star follows the same elegant laws whether the clock is ticking forward or backward. In the silent language of physics, there is no inherent arrow of time. So why does our world scream with its direction? We never witness a splattered egg leaping from the floor to reassemble perfectly in our hand. We never feel ourselves grow younger, our memories unwinding into the unknown. This is the great disconnect, the central paradox of time's arrow. Our everyday experience is irreversible, a one-way street, while the underlying mechanics appear to be a two-way road. Think of watching a movie played in reverse. A diver does not arc gracefully into the water, but is violently ejected from it, flying backward onto the diving board. We instantly recognize this as absurd, as wrong. Our universe on the grand stage only plays the film in one direction. The mystery is not just why we move forward, but why we cannot move back when the most basic laws of physics suggest that we should be able to. This paradox finds its resolution not in the rules of planets or particles, but in a grander, more statistical truth. The universe possesses a built-in bias, a preference for moving toward states that are simply more likely. This is the domain of entropy, often described as disorder. That word can be misleading. Entropy is better understood as a measure of possibility. It counts the number of ways the microscopic components of any system can be rearranged while still looking the same from the outside. Think of a brand new deck of cards fresh from the box. The suits are in perfect order, a state of low entropy. There is essentially only one way for the deck to be arranged to appear that pristine and ordered. Now shuffle that deck just once. You have created a high entropy state. The cards are now in a random sequence, one of an almost unimaginable number of possible sequences. A perfectly ordered deck is a rare, fragile, and improbable situation. A shuffled deck is a common, robust, and overwhelmingly probable one. The universe, much like that deck of cards, constantly moves from less probable arrangements to more probable ones. This relentless drift is enshrined in the second law of thermodynamics, which states that the total entropy of any isolated system always increases. It never decreases. To see this law in action, picture a single drop of ink falling into a clear glass of water. At first, the ink is concentrated, a tidy blob of dark color in a sea of clear. This is a state of low entropy, but then the inevitable happens. The ink begins to spread. It swirls and diffuses, its molecules exploring every available millimeter of water until the entire glass holds a uniform, faintly tinted liquid. The system has reached a state of high entropy. The molecules of ink and water are now mixed in one of the vast number of possible mixed configurations. You will never, ever see all those scattered ink particles spontaneously decide to swim back together, coalescing into a single, dense drop in the center of the glass. That reverse process would require entropy to decrease, violating the universe's most stubborn rule. This irreversible slide from order to disorder, from low probability to high probability, is the physical mechanism that gives time its arrow. It is the reason we remember the past but not the future. The past is the state of lower entropy, the single, neat stack of cards. The future is the state of higher entropy, the shuffled deck. The great cosmic film can only roll in one direction because the universe is constantly progressing toward more statistically likely arrangements of its energy and matter. Entropy broke the symmetry, pointing time forward on a one-way journey. So how did the universe find itself holding that perfectly ordered deck of cards? The ultimate source of time's arrow lies in a single, monumental event, the Big Bang. Our entire cosmic story, this relentless flow from past to future, began with a starting condition of breathtakingly low entropy. Picture the universe in its first fleeting moments, a searingly hot and dense soup of energy and fundamental particles. It was remarkably uniform, a nearly smooth and featureless sea. This smoothness is the key. While it might seem chaotic, this uniform state was paradoxically a state of extremely low entropy. Think back to the glass of water. The unmixed state, with the ink concentrated in one place, is the low entropy one. The early universe was like that, but on a cosmic scale. All of its energy and matter were packed together in a state of gravitational potential that was incredibly uniform and therefore highly ordered. There were no stars, no galaxies, no clusters, just a hot, dense, and smooth primordial fireball. This was the universe's pristine, unshuffled deck. Out of all the possible ways the cosmos could have begun, it started in this peculiarly simple and organized configuration. And from that singular moment, the only direction to go was toward higher entropy. The universe had to evolve, it had to mix. Gravity began to pull matter into clumps, forming the first stars and galaxies, creating intricate structures from the smooth initial conditions. This process of structure formation is a massive engine for increasing entropy. The smooth beginning was the low probability starting gun, and the chaotic, structured universe we see today is the high probability outcome we are still racing toward. Every second that ticks forward is a testament to that initial state. The reason you remember yesterday and not tomorrow is because yesterday was part of a universe with lower entropy, closer to that impossibly ordered beginning. The entire forward march of time, from the cooling of the cosmos to the burning of stars and the lives of civilizations, is just the universe playing out the consequences of that one low-entropy start. But this cosmic drift toward disorder presents us with a beautiful puzzle. If entropy always increases, why do we see such magnificent structures in the sky? Galaxies spiral in vast assemblies, stars ignite in sustained fusion, and planets coalesce into ordered spheres. This seems like the very opposite of things falling apart. The resolution to this paradox lies with the most familiar yet most mysterious force in the cosmos, gravity. In the grand accounting of cosmic entropy, gravity plays by its own unique set of rules. It is the master architect of the universe, and its work profoundly drives time's arrow forward. Recall the early universe, that hot, dense, and incredibly smooth primordial soup. In terms of gravity, this uniformity was a state of extremely low entropy. A cloud of gas spread evenly throughout space has vast amounts of gravitational potential energy, but it is all potential, a quiet and ordered state. Gravity abhors this uniformity. It is an unstoppable force that seeks to clump matter together. As the universe expanded and cooled, tiny ripples in the density of matter provided the seeds for gravity to work its magic. It began pulling particles together, creating the first stars and galaxies from the featureless void. This seems like the creation of order from chaos, but in the precise language of physics, it is a massive and dramatic increase in gravitational entropy. Think of it this way: a diffuse, scattered cloud of gas has relatively few ways its particles can be arranged gravitationally. But when that cloud collapses under its own weight to form a dense, hot star, the situation changes completely. The star has concentrated a tremendous amount of mass into a small volume, releasing a flood of energy in the process, energy that radiates out into the cold emptiness of space. This entire process, from a sparse cloud to a brilliant star, has created a far more probable and disordered state for the overall system. The energy that was once stored neatly as gravitational potential is now dissipated as heat and light, spreading out and increasing the universe's total entropy in a spectacular way. The ultimate expression of this is a black hole. A black hole is the highest entropy object possible for a given amount of mass. It is the final, most probable state for matter and energy under the relentless pull of gravity. So the formation of every star, every galaxy, and every black hole is not a violation of the second law. It is its most powerful expression on the grandest stage. Gravity is the engine that takes the smooth, low-entropy beginning of the universe and uses it to build the complex cosmos we see today, all while ruthlessly turning the wheels of the cosmic clock. The intricate structures we admire are not exceptions to time's arrow. They are its direct consequence, temporary waystations on the long road to maximum disorder. Our own minds are caught in this same irreversible current. We perceive time as a continuous stream, flowing from the past we recall toward a future we can only anticipate. This is the psychological arrow of time, our internal experience of the cosmic clock. The question is profound: why do we remember yesterday with such clarity, but have no memory of tomorrow? The answer lies not in some mystical property of consciousness, but in the physics of the brain itself. Your brain is a physical object, a complex network of neurons that consumes energy and generates heat. It is a thermodynamic system, and it is subject to the same universal laws that govern the spreading ink drop and the collapsing gas cloud. When you form a memory, your brain undergoes a physical change. Neural connections strengthen or weaken, and new pathways are forged. This process requires energy, and like all processes, it increases the total entropy within your head. The memory trace itself is a particular, ordered configuration of neural activity, but creating it dissipates energy as heat, contributing to the universe's overall disorder. You cannot remember the future because a memory of tomorrow would be an effect without a cause. It would mean your brain's neural state had been influenced by an event that has not yet happened, a configuration that would require entropy to spontaneously decrease. This is as statistically impossible as all the ink particles in the glass deciding to swim back into a single drop. Our perception of a flowing present, the relentless march from one moment to the next, is our consciousness riding the wave of increasing entropy. The past feels fixed because it is a state of lower entropy, a recorded sequence of cause and effect. The future feels open and unknown because it is a state of higher entropy, one of countless possibilities yet to be narrowed down by the unfolding of events. Your very sense of self, built upon an accumulating library of memories, is a direct and intimate consequence of the universe's one-way journey from order to disorder. This expansion of space itself carves out another fundamental arrow of time, one written across the entire cosmos. We call this the cosmological arrow, and its evidence is visible in the light from every distant galaxy. As the universe stretches, it carries these galaxies away from us, and the light they emit is stretched along with space, shifting its color toward the red end of the spectrum. This redshift is the universe's fingerprint, a permanent record of its ongoing growth. The cosmological arrow is not a separate phenomenon from the relentless rise of entropy. It is its ultimate enabler. The expansion of space provides the room and the conditions for disorder to increase. As the universe grows larger, it cools down, creating the temperature differences that power stars and drive the complex processes of life and structure formation. Without this cosmic stretching, the universe would remain a hot, dense, and uniform soup, a state of equilibrium where little could happen and time's arrow would lose its meaning. This leads to a mind-bending question. If the expansion of the universe were to halt and reverse, if space itself began to contract, would the arrow of time flip? Would we see shattered glass reassemble and memories flow backward? The idea is captivating, suggesting a cosmic symmetry where a big crunch mirrors the Big Bang. Yet most modern cosmological evidence points toward a different, more permanent fate. The universe's expansion appears to be accelerating, not slowing, driven by a mysterious dark energy. A future contraction seems unlikely. Even if it did happen, many physicists argue that the thermodynamic arrow, the drive toward higher entropy, would not reverse. A contracting universe would likely be a chaotic, high-entropy environment where time's one-way street would continue, leading to a final hot collapse. The direction of time seems irrevocably set by that initial low-entropy state, a one-way ticket on a journey that is still unfolding. Down in the quantum realm, the rules of reality bend, and time itself faces a new kind of test. The physics of the very small introduces its own arrow of time, one that is tied not to gravity or thermodynamics, but to the very act of seeing. This is the puzzle of the quantum arrow. In our everyday world, objects have definite properties. A ball is either here or there, but for a tiny particle like an electron, this certainty vanishes. Before it is measured, a particle exists in a state called a superposition. It is not in one place or with one specific property, but is spread out in a cloud of potential, a blend of all its possible states at once. This cloud is described by the wave function, a mathematical entity that holds all the probabilities for what the particle could become. The act of observation, the moment we measure the particle, forces this cloud of possibilities to collapse. The wave function seems to vanish, and the particle snaps into a single, definite reality. An electron that was both here and there suddenly appears in one specific location. This process, the collapse of the wave function, is starkly irreversible. You cannot unmeasure a particle. You cannot take that definite result and coax it back into its fuzzy, probabilistic state. This transition from a multitude of maybes to a single, concrete fact creates a tiny, fundamental arrow of time with every observation we make. The classic thought experiment of Schrödinger's cat makes this strange idea tangible, though not with a real feline. Imagine a cat sealed in a box with a perilous quantum device. A single radioactive atom is linked to a mechanism that will release a poison if the atom decays. According to quantum rules, the atom exists in a superposition. It is both decayed and not decayed at the same time. Therefore, until someone opens the box and looks inside, the cat must also be in a superposition. It is, in a quantum sense, both alive and dead. This seems absurd, and that is the point. The moment you lift the lid, your observation collapses the wave function. The superposition is destroyed. You find the cat definitively alive or definitively dead. There is no in-between, and there is no going back. You have created a new, irreversible fact in the universe. The transition from the strange blend of alive and dead to a single, certain outcome is a one-way street. It carves another groove pointing time forward. Could this quantum measurement problem be the ultimate source of time's arrow? Some physicists speculate that wave function collapse is the most primitive engine of time, the fundamental click of the cosmic clock from which all other arrows emerge. Every observation, every interaction that forces a quantum possibility into a classical fact is a tiny stitch in the fabric of a flowing present. It suggests that time may not be a background stage on which events play out, but something that is built moment by moment from an endless sea of quantum decisions. Yet even the quantum arrow seems to follow a deeper, more fundamental command. At the very heart of physics lies a principle of such elegance it was long considered unbreakable, the sacred symmetry known as CPT. This stands for charge, parity, and time. The idea was breathtakingly simple. If you could perform 3 simultaneous transformations on the universe, if you reversed the flow of time, swapped left for right in a mirror-like reflection, and replaced every particle with its antimatter counterpart, the laws of physics would remain utterly unchanged. The cosmos would, in principle, run just as well backward as it does forward. This CPT theorem was a cornerstone of modern physics, suggesting that deep down reality was perfectly balanced and reversible. But then, experiments began to chip away at this perfect symmetry. The first crack appeared not with time but with a mirror. In the 1960s, physicists James Cronin and Val Fitch made a shocking discovery while studying particles called kaons. They found that the combined symmetry of charge and parity, CP, was subtly violated. The behavior of these particles was not perfectly mirrored when matter was swapped for antimatter. The universe, it seemed, had a tiny but measurable preference for one version of reality over its mirrored opposite. This was a monumental finding that earned them the Nobel Prize. And because of the ironclad CPT theorem, if CP symmetry is broken, then time reversal symmetry, the T in CPT, must also be broken to keep the overall balance. The violation of CP symmetry forces a violation of time symmetry. This means the laws of physics themselves are not perfectly indifferent to the direction of time. At the most fundamental level of particle interactions, the universe can tell the difference between forward and backward. This is not a statistical preference like entropy, but an intrinsic bias written directly into the script of reality. The implications are staggering. There is a built-in arrow of time woven into the fabric of the forces that govern every particle. This tiny asymmetry in the early universe may even help explain one of the greatest cosmic mysteries, why we live in a world made almost entirely of matter, when the Big Bang should have created equal amounts of matter and antimatter. The slight favoritism for matter over antimatter, a direct result of CP violation, could be the reason anything complex, including us, exists at all. So time's arrow is not merely an emergent property of a vast statistical universe. It is etched into the very laws of physics, a fundamental lopsidedness that guides the cosmos from its smallest interactions to its grandest scales. This profound bias in the laws of physics finds its ultimate expression in the darkest objects in existence. Black holes are not merely cosmic vacuum cleaners. They are the universe's ultimate entropy sinks, the final destination for disorder. The work of physicists Jacob Bekenstein and Stephen Hawking revealed a truth so counterintuitive it reshaped our understanding of reality. They discovered that the entropy of a black hole, the total disorder it contains, is not related to the volume of space inside it, but to the surface area of its event horizon, the point of no return. This was a revolutionary idea. In our everyday world, entropy is a volume-based property. The more space you have, the more ways you can disorder the things inside it. But for a black hole, all the information about the stars, planets, and gas it has consumed is somehow encoded on its two-dimensional boundary. It is as if the entire three-dimensional contents of a library were perfectly projected onto its spherical walls. This area law for entropy suggests that space itself may be fundamentally pixelated, built from tiny, indivisible units, a concept that continues to drive the search for a theory of quantum gravity. Black holes are the most efficient processors of chaos in the cosmos. When ordered matter, like a star, falls past the event horizon, it is not simply erased. Its immense gravitational energy and information are converted, according to Hawking's calculations, into a faint whisper of thermal radiation that slowly leaks back out into the universe. This Hawking radiation is pure disorder, a random, featureless heat. The black hole has taken a complex, structured object and transformed it into the most randomized form of energy possible, dramatically increasing the universe's total entropy in the process. The entire life cycle of a black hole, from its violent birth in a supernova to its achingly slow evaporation over trillions of years, is a powerful engine for time's arrow. Its formation creates a massive leap in gravitational entropy, and its eventual disappearance via Hawking radiation leaves behind only a more disordered cosmos. These celestial phenomena are not exceptions to the rule. They are the rule written in the most extreme possible terms, defining the thermodynamic destiny of everything. This brings us to the deepest and most perplexing question of all. Why was the universe handed that perfectly ordered deck of cards to begin with? The initial low-entropy state is not explained by any known law of physics. It is simply assumed as the starting point. Physicists call this the past hypothesis, and it stands as one of the greatest unsolved puzzles in science. The laws we have, from gravity to quantum mechanics, are magnificent at telling us how the universe evolves from a given state. But they are utterly silent on why the first state was so peculiarly simple and uniform. It is as if we have discovered the precise rules of a movie projector, understanding every gear and lens, but we have no idea why the first frame of the film was a blank white screen. This singular moment of low entropy is the ultimate cause of everything that followed. The reason time has a direction and history has a shape. Without it, the cosmos would be a formless, timeless equilibrium, a soup with no stories. So why did it happen? One compelling, if humbling, idea is the anthropic principle. This suggests that our very ability to ask this question depends on the universe having these specific conditions. We exist in a cosmos that allows for stars, planets, and life because we are the products of its particular history. In a vast multiverse, a sprawling collection of countless universes, each with different physical laws and initial conditions, most would be stillborn. They might collapse instantly or remain a featureless gas, never forming complex structures. We find ourselves in one of the rare universes where the starting conditions were just right for entropy to increase slowly, allowing for billions of years of cosmic evolution and the emergence of conscious observers like us. In this view, the low-entropy beginning was not a planned event, but a cosmic lottery ticket we happened to draw. Another, more radical possibility is that our low-entropy Big Bang was not a true beginning at all. Perhaps it was a random, colossal fluctuation. Even in a state of maximum disorder and heat death, the laws of quantum mechanics allow for the spontaneous, if unimaginably rare, appearance of order. Given enough time, a universe in thermal equilibrium could, by pure chance, fluctuate into a state of low entropy, much like all the air in a room spontaneously gathering in one corner. From our perspective inside that fluctuation, it would look exactly like a Big Bang, initiating a new arrow of time and a brief period of structure and life before dissolving back into chaos. Our entire cosmic history, from the first stars to this very moment, could be a temporary island of order in an eternal sea of randomness. Or perhaps the answer lies in a theory that unites gravity and quantum mechanics, a framework that describes the moment of creation itself. In such a theory, the smooth, low-entropy early universe might not be a mysterious starting assumption, but a natural and necessary outcome of a deeper physics we have yet to uncover. The search for this ultimate explanation continues, driving the frontiers of cosmology and fundamental physics. The past hypothesis is more than a scientific problem. It is a profound reminder of our place in the cosmos. Our entire reality, the flow of time we feel in our bones, and the very fact that we can look back on a past, rests on a foundation that remains, for now, a beautiful and haunting mystery. But this cosmic journey from order to disorder confronts a radical and beautiful idea from Einstein's own work. His theory of relativity paints a picture of reality not as a flowing river, but as a solid, four-dimensional block. In this block universe, the past, present, and future are not successive. They simply are. Every event that has ever happened or ever will happen is fixed in its place within this vast, static structure of space-time. Your birth, your first memory, and every moment yet to come already exist, permanently etched into the cosmic fabric. This view shatters our most basic intuition. It suggests that the flowing present, the feeling of time passing, is a powerful illusion generated by our consciousness. We are like readers moving through a book, experiencing one chapter at a time, even though every page already exists complete and unchanging. If this is true, then where does time's arrow point in a universe where everything just is? The answer lies in the block itself. Even in a static reality, the block has a structure. It is not a formless lump. There is a distinct gradient, a fundamental slope that runs from one end to the other. At one end of the block, the universe is in a state of incredibly low entropy, that smooth, dense beginning. At the other end, it is in a state of maximum entropy, a vast, dark, and uniform equilibrium. Our conscious journey through the block, the illusion of a moving now, is not a random drift. It is a traversal along this entropy gradient. We are wired by the laws of physics and the nature of memory to perceive the universe in the direction of increasing disorder. Causality, the unbreakable chain where cause must always precede effect, is the thread that guides us. You remember the past and not the future because along the path your consciousness takes, the past always has lower entropy. It is the domain of causes. The future is the domain of effects, the state of higher entropy toward which everything inevitably trends. Think of the block universe as a steep, rugged hillside. The entire hillside exists at once, from the ordered peak to the disordered valley below. Our conscious experience is like a single drop of water, always and only flowing downhill, following the path of the entropy gradient. We cannot flow uphill because that would mean experiencing effects before their causes, remembering events that haven't happened yet. The block universe does not erase time's arrow, it explains its persistence. The arrow is not the motion of time, but a permanent feature of spacetime's geometry, a one-way street built into the very architecture of reality that our minds are compelled to follow. This means your life, with all its past regrets and future hopes, is a complete and timeless story. Yet from within, it feels like a dynamic and unfolding mystery, a journey along a slope that was set at the very dawn of creation. This unbreakable chain of cause and effect is the very scaffold of our reality. A baseball must fly through the air before it shatters a window. A decision must be made before its consequences unfold. But why is this sequence so absolute? The answer is carved into the fabric of spacetime itself by a structure known as the light cone. Imagine every single event in the universe, from the blink of your eye to the explosion of a star, as a point in the four-dimensional block. From that point, we can draw a map of its possible influence. This map is its light cone. The future light cone contains every point in spacetime that could potentially be affected by that event. Since no information or influence can travel faster than light, these points are only those that a beam of light or something slower could reach from the event. Conversely, the past light cone contains every event that could have possibly influenced it. Anything outside these cones is forever disconnected, existing in a realm of absolute elsewhere where no causal link is possible. This elegant structure is relativity's way of enforcing the cosmic rule that cause must always come before effect. It physically prevents an event in what we call the future from influencing an event in what we call the past. The light cone geometry makes the sequence of cause and effect a fundamental feature of the universe's architecture, but this is only half the story. Why do causes always create effects that increase disorder? A thrown baseball is a localized, ordered motion. The shattered window is a disordered spray of glass fragments. The cause is a state of lower entropy, and the effect is a state of higher entropy. The thermodynamic arrow provides the raw material for causality to work with. For a cause to leave a lasting, unambiguous mark on the world, it must create a record, and creating any record is an irreversible process that increases entropy. Think of your own memory. The event of reading this sentence is the cause. The physical change in your brain that forms the memory is the effect. That neural change dissipates energy and increases disorder within your head. If entropy could freely decrease, those memory traces could spontaneously unravel, blurring the line between cause and effect until the very concept became meaningless. You could have a memory of an event that never actually happened. The light cone structure dictates what events can influence each other, but the relentless rise of entropy dictates the irreversible nature of that influence. It ensures that causes leave permanent scars on the universe, scars that point decisively from the past toward the future. Our direct experience of time, flowing from cause to effect, is our consciousness navigating this dual landscape, a world where the geometry of space-time and the statistics of disorder align perfectly to create a single, unambiguous arrow. This brings us to the final frontier of the mystery, the observer who watches the cosmic clock tick. Is the flow of time a real, physical feature of the universe, or is it a magnificent illusion woven by our own minds? We have explored the thermodynamic, cosmological, and quantum arrows, but we are left with the hard problem of consciousness itself. Why does reality feel like a continuous, flowing stream instead of a series of disconnected snapshots? Some thinkers, like physicist Julian Barber, propose a radical answer. He argues that time does not exist at all. There is no past or future, only an infinite collection of timeless moments, a vast landscape of nows that we mistakenly perceive as a sequence. In this view, our entire lives are a single, permanent sculpture, and the feeling of movement is a trick of perception. If this is true, then the arrow of time is not a property of the cosmos, but a story told by our brains. So how does the brain construct this story? Your mind is not a passive camera recording a flowing reality. It is a relentless prediction machine, constantly building and updating a model of the world. Your senses provide raw, disjointed data, a chaotic stream of sights, sounds, and smells. Your brain's job is to take this chaos and weave it into a coherent narrative, a single, seamless timeline of experience. It does this by making countless tiny predictions about what should happen next, and then correcting its model based on what actually occurs. The sensation of a moving present moment is the feeling of this model being updated over and over again. Think of it like a ship navigating a foggy sea. The ship's captain has a map, a mental model of where they are and where they are going. As new landmarks appear through the fog, the captain updates the map. The feeling of journeying forward is the feeling of that map being constantly revised. Your consciousness is that captain, and the flow of time is the sensation of your internal map being redrawn with each new piece of sensory information. This process is deeply tied to memory. Your brain stores the previous versions of its model, and that stored record is what we call the past. The future is the brain's projection, its best guess for the next update. This beautifully bridges the gap between the objective physics of the block universe and our fiery, subjective experience of life. The block universe provides the permanent, four-dimensional landscape. Our conscious brains provide the journey, the single, glowing point of awareness that moves through that landscape, forever updating its map along the path of increasing entropy. This forces a profound question. If every conscious being vanished from the cosmos, would time still have a direction? From a purely physical perspective, the entropy gradient would remain. The universe would still be evolving from its smooth beginning toward its disordered end. The light cones would still enforce causality, but without a mind to traverse that slope, to build a model and feel it update, would there be anyone to call it an arrow? The flow, the sensation of passage, requires a flower. The universe provides the stage and the script, a timeless story etched into space-time. But it is consciousness that provides the reader, the one who experiences the story, one unforgettable word at a time. To grasp the true origin of time, we must step beyond our current understanding. General relativity paints a magnificent picture of gravity shaping the cosmos on the grandest scales, while quantum mechanics reveals the bizarre, probabilistic rules of the very small. Yet these two pillars of modern physics are fundamentally at odds. Unifying them is perhaps the greatest challenge in all of science, a quest for a theory of quantum gravity. This is not just an academic exercise, it is a search for the rulebook that governed the universe in its very first moments, when all of reality was smaller than a single atom. Leading candidates for this ultimate theory, like string theory and loop quantum gravity, propose ideas that radically reshape our concept of time itself. They suggest that time, as we experience it, may not be a fundamental ingredient of reality. Instead, it could be an emergent property, a collective behavior that arises from a more basic, timeless layer of existence, much like the sensation of wetness emerges from the collective motion of countless individual water molecules. In this view, the flowing river of time is not the fundamental reality, but a powerful illusion created by the underlying interactions of a world without time. This leads to breathtaking possibilities for our cosmic origin. One compelling idea is the concept of a big bounce. Perhaps our Big Bang was not a singular creation from nothing, but a monumental rebound. In this scenario, a previous universe very much like our own eventually collapsed under its own gravity in a big crunch. But instead of vanishing into a point of infinite density, the extreme quantum nature of reality at that scale caused a rebound, a cosmic bounce that gave birth to our own expanding universe. In such a model, time's arrow might not have been a constant. The previous universe could have had its own direction of time, perhaps even pointing backward from our perspective, before the bounce reset the cosmic clock and sent it spinning forward again on our current path. Other theories propose the Big Bang was not a beginning at all, but a phase transition, a shift in the state of reality as profound as water freezing into ice. Our universe, with its 4 dimensions of space-time, could have crystallized from a more primitive, higher-dimensional reality where our familiar concepts of before and after simply did not apply. The initial low-entropy state that gave time its arrow would then be a natural consequence of this freezing process, a cosmic seed from which our entire history grew. These are not just wild speculations, they are the rigorous mathematical frontiers of theoretical physics, attempts to answer the question that haunts our understanding of existence. Why is there something with a past, a present, and a future rather than nothing or a timeless, static eternity? The search for quantum gravity is the search for the engine of time itself, a journey to the very precipice where causality begins and our story was first written. So we are left with a universe whose history depends entirely on a single, inexplicable starting point. But what if this apparent fine-tuning is not a cosmic accident, but a necessary condition for our own existence? This is the core of the anthropic principle, a line of reasoning that turns the mystery of time's arrow back on us, the observers. The principle suggests a simple yet profound truth. The universe has a strong, forward-pointing arrow of time because if it did not, we would not be here to notice its absence. Consider the ingredients required for life as we know it. We need stable stars that burn for billions of years, providing a constant flow of energy. We need planets to form from the debris of stellar explosions, offering stable platforms for chemistry to become biology. We need biological processes like metabolism, reproduction, and evolution, all of which are fundamentally irreversible engines that consume energy and increase disorder. None of this is possible in a universe where time's arrow is weak or non-existent. Imagine a cosmos that began in a state of high entropy, a chaotic and mixed-up soup from the very start. In such a place, there would be no temperature differences to drive the formation of galaxies. Stars would not ignite, or if they did, they would fizzle out instantly in a sea of uniform heat. Planets could never coalesce from the disorder. Life, which depends on a relentless flow of energy from orderly states to disorderly ones, would be an impossibility. The very processes of thought and memory, which rely on irreversible changes in the brain, could not function. A universe without a clear past and future is a universe without stories, without history, and without observers. This connects directly back to the past hypothesis, that mysterious low-entropy beginning. The anthropic principle does not explain why that initial state occurred, but it does explain why we find ourselves in a universe that had one. In a hypothetical multiverse, a vast collection of cosmic domains with different physical laws and initial conditions, most would be stillborn. They might collapse immediately into black holes or expand so rapidly that no structures could form, or simply remain in a lukewarm, timeless equilibrium. We, by definition, can only exist in one of the rare, lucky universes where the initial entropy was low enough to allow for a long and complex cosmic evolution. Our arrow of time is not a universal standard. It is our specific, local address in a much wider cosmic landscape. It is the unique signature of a universe that won the lottery, a cosmos where the conditions were just right for the slow, beautiful, and irreversible dance of life to begin. Science fiction loves to play with a backward-flowing clock. From novels to blockbuster films, we see characters aging in reverse, speaking sentences that begin with the last word, and receiving warnings from a future that has not yet happened. These are captivating ideas, but what would such a reality truly entail according to the laws of physics? If the arrow of time were reversed, the universe would not be a simple rewind of our own. Every fundamental process would be inverted. Gravity would suddenly become a repulsive force, pushing matter apart. Stars would not draw their fuel from nuclear fusion, but would instead absorb cold light from the void, growing hotter and denser until they collapsed into pristine clouds of hydrogen. The most profound change, however, would be in the fabric of causality itself. Effects would precede their causes. A shattering wine glass would leap from the floor, its fragments soaring upward to reassemble perfectly in your hand, and only then would you release your grip. The scar on your knee would appear spontaneously, and a moment later, the fall that caused it would happen. This is not just a world running in reverse, it is a world where logic itself is turned inside out. But here lies the deepest puzzle. If you were a conscious being living inside this backward universe, what would you actually experience? Your brain, a physical object that operates on thermodynamic principles, would also be running in reverse. In a world of decreasing entropy, your memories would not be formed from past events, but would instead be pre-existing impressions of a future that is destined to happen. You would wake up each morning with a perfect memory of the entire day ahead, a day you have not yet lived. As the hours passed, those memories would fade one by one until you fell asleep knowing nothing. Your conscious experience would feel perfectly normal and continuous to you because your brain's internal model of the world would be updating along the local arrow of time. You would perceive your strange universe as the only reality, believing that causes still precede effects, even though from our perspective the opposite is true. This reveals a startling truth. The flow of time is not an absolute feature of the cosmos, but a perspective locked to the local direction of the entropy gradient. We do not perceive time, we perceive entropy. This thought experiment shows why messages from the future remain a fantasy. For a signal to travel backward in our time, it would need to carve a path of decreasing entropy, a bubble of reversed causality within our forward-flowing world. The moment such a signal interacted with our environment, it would create a paradox. Imagine a message from tomorrow tells you not to leave your house today. You heed the warning and stay home, but if you never leave, what caused the message to be sent? The event of receiving the information prevents its own cause from ever occurring. Physics resolves this not with mystery, but with statistics. The probability of a macroscopic signal composed of trillions of atoms spontaneously arranging itself into a coherent message from a future state is so infinitesimally small that it is effectively zero. The universe favors stories that make sense, narratives where causes lead to effects and entropy always increases. Our one-way street of time is not just a physical rule, it is the very foundation of a coherent reality, a story that can only be read from beginning to end. The evidence for time's arrow is not locked away in abstract theory. It is written into the world around us in ways we can directly observe and measure. Consider a simple cup of coffee left on a counter. You never witness its heat concentrate, drawing warmth from the room to become scalding hot once more. It always cools, its thermal energy dissipating into the environment, increasing the disorder of the universe in a small but definitive act. This is entropy in action, a daily demonstration of the one-way street we all inhabit. Our own bodies provide another constant testimony. We age, our cells accumulate damage, our skin loses its elasticity, and we cannot reverse the process. Biological aging is a symphony of irreversible chemical reactions, each one a step toward a state of higher entropy, confirming that for living systems the clock only ticks forward. These mundane experiences are profound, for they are local echoes of the universe's ultimate trajectory. On a cosmic scale, the most powerful evidence comes from the afterglow of creation itself, the cosmic microwave background radiation. This faint, uniform heat that permeates all of space is a fossilized snapshot of the universe when it was just 380,000 years old. Its incredible smoothness is the smoking gun for that initial low-entropy state. This relic radiation shows us a cosmos that was remarkably uniform and ordered, a pristine starting condition from which all the complexity we see today could unfold. The existence of this fossilized background is observable, measurable proof that the universe began in a special, organized configuration, setting the arrow of time in motion. But the most startling confirmation comes from the world of the very small, from particle physics experiments. In the 1960s, scientists studying neutral K mesons, a type of subatomic particle, witnessed something extraordinary. These particles and their antimatter counterparts decayed in a slightly different manner. This was a clear violation of CP symmetry, where C stands for charge and P for parity. Because the combined symmetry of CPT must always hold according to our fundamental theories, the breaking of CP symmetry forces a violation of time reversal symmetry, the T. This means the laws of physics themselves are not perfectly symmetrical in time. There is a built-in bias, an intrinsic arrow, written into the behavior of the fundamental forces that govern every particle. We have not just inferred time's direction from large-scale statistics, we have measured its fundamental lopsidedness in the laboratory. From the cooling of your morning coffee to the fading echo of the Big Bang and the subtle decay of a single particle, the forward march of time is a fact confirmed by every layer of reality we can probe. This philosophical rift forces us to confront the very nature of existence. Is the future already out there, a destination waiting for us to arrive, or are we actively building it with every choice we make? The block universe view, known as eternalism, argues that past, present, and future are equally real. Your entire life is a completed sculpture in the four-dimensional block of spacetime. The opposing view, presentism, insists that only the present moment is real. The past is gone, a ghost, and the future is pure potential, not yet written. A third idea, the growing block theory, offers a compromise, suggesting that the past and present are real and fixed, while the future remains an open frontier, constantly being added to the growing structure of reality. This is the concept of becoming, the profound sense that the universe is perpetually coming into existence, moment by moment. It is the feeling that the future is not a place but a process. Where does the arrow of time fit into this ancient debate? The block universe elegantly contains the arrow as a permanent feature, the entropy gradient from one end of the block to the other. But it struggles to explain our raw, fiery experience of a flowing now. Presentism and the growing block theory place that flowing now at the very heart of reality, suggesting that the passage of time is a fundamental, active force in the cosmos. They argue that the universe is not a static thing, but a dynamic event, a continuous act of creation. Think of a potter at a wheel. the block universe sees the finished pot complete and unchanging. The philosophy of becoming is focused on the spinning wheel, the wet, pliable clay taking shape under the potter's hands, a process that is alive and happening right now. Our scientific understanding of entropy provides the raw material for this creation. The relentless increase in disorder carves a channel, a one-way street that gives the process of becoming its direction and its irreversibility. It ensures that the universe is writing a story that cannot be erased, adding new pages to the book of reality that can never be torn out. This connects our most advanced physics to the oldest questions humanity has ever asked. Are we passengers on a cosmic train ride, watching a predetermined landscape scroll past the window, or are we the engineers laying down the tracks of reality just ahead of our own movement? The feeling that you are reading these words in a genuine present, that your next thought is not already etched into some cosmic record, is the visceral experience of becoming. It is the sensation of the future being forged in the furnace of the now. Perhaps the flow of time is not an illusion, but the deepest truth of all, the universe's way of bringing new things into being forever. Every thought you have, every memory you recall, is a physical thing. Information is not an abstract concept. It is etched into the world through the arrangement of atoms, the spin of electrons, and the state of countless microscopic components. This reveals a profound connection between what we know and the relentless flow of time. The relationship between information and entropy is inseparable. When entropy increases, when a system becomes more disordered, specific information is irretrievably lost. Think back to the drop of ink diffusing in a glass of water. At the beginning, you know the precise location of every ink molecule. As they spread and mix, that detailed information vanishes into the chaos. You are left only with the general knowledge that the water is tinted. The universe has forgotten the intricate starting configuration. This irreversible loss of information is not a side effect of time's arrow. It is the very mechanism that carves its groove. This leads us to a brilliant and famous challenge to this entire idea, a thought experiment known as Maxwell's demon. Imagine a tiny, intelligent creature guarding a small door between two chambers of gas. This demon can see individual molecules approaching. When a fast, hot molecule comes from the left, it opens the door to let it into the right chamber. When a slow, cold molecule comes from the right, it lets it into the left. By doing this, the demon seems to be sorting the molecules, creating a hot chamber and a cold chamber without doing any work. It appears to be decreasing the entropy of the system, reversing the arrow of time simply by using information. For decades, this demon haunted physicists. How could a being with perfect knowledge seemingly defy the second law? The resolution to the paradox lies in the demon itself. To see a molecule and decide whether to open the door, the demon must gather information. It might use a tiny flash of light to illuminate the molecule. That act of measurement of acquiring the data is a physical process. The light particle bounces off the molecule and into the demon's eye or sensor. That collision transfers energy and generates a tiny amount of heat. More importantly, the demon's brain or its memory must now store this new piece of information. Storing information is a physical act that requires energy and increases entropy inside the demon. When you add up all the entropy, the disorder created by the demon's process of measuring, remembering, and eventually erasing its old data to make room for new observations, the total entropy of the entire system, demon and gas chambers combined, always increases. The demon is not a magician, it is a participant, and its own thermodynamic cost is the price of doing business. It cannot break the second law, it merely enforces it in a more sophisticated way. This deepens our understanding immensely. The processing of information, from the simplest measurement to the most complex calculation, is an irreversible act that fuels time's arrow. Every time you learn something new, your brain increases the universe's total entropy. every time a computer deletes a file, it releases a tiny puff of heat into the cosmos, a small sacrifice to the relentless demand for disorder. The flow of time is, in a very real sense, the flow of information from a state of specific, known details to a state of generalized, forgotten history. We are not just moving through time, we are processing it, and with every thought we pay the cosmic price that keeps the clock ticking forward. This bleak but fascinating final state is known as the heat death. All the cosmic drama we see today, from the nuclear furnaces of stars to the intricate dance of life, is a temporary rebellion against this ultimate fate. Picture the universe in a trillion years. The last stars have long since burned out, their ashes scattered. Black holes, once the ultimate symbols of power, have evaporated into faint whispers of radiation through Hawking radiation. What remains is a near-perfect vacuum, a cosmos so vast and empty that the distance between any two surviving particles is astronomically large. The temperature throughout all of space is just a fraction of a degree above absolute zero, a state of profound and uniform cold. In this final equilibrium, the universe has reached maximum entropy. Every possible energy gradient has been leveled out. There are no hot spots and no cold spots. There is no fuel left to burn, no difference in temperature to exploit, and therefore no possibility of doing any work. A universe that can do no work is a universe where nothing happens. No stars ignite, no planets form, no chemical reactions occur. The cosmos becomes a static, eternal sea of lukewarm, ultra-diffuse particles and radiation, unchanging for eons beyond human comprehension. In such a state, the arrow of time faces its own extinction. Time's direction is defined by change, by the progression from one state to another. But in the heat death, there are no meaningful states left to transition between. With no processes to mark a before and an after, the concepts of past, present, and future lose their anchor. The cosmic clock, set in motion by the low-entropy Big Bang, finally winds down to a stop. There is no tick and there is no talk. There is only a silent, endless now, a universe where time itself has become meaningless. This is the ultimate destination of the one-way street we are traveling, the final, quiet conclusion to the story that began with a single, ordered breath. But what if our entire experience of time is a shadow? The physics we have explored so far, from entropy to quantum collapse, all operates within the framework of a single, flowing time. Yet a small group of theoretical physicists is asking a far more radical question. What if this one-dimensional timeline we are so certain of is merely an illusion, a simplified projection from a far richer, timeless reality? One of the most mind-bending proposals is the idea of a two-time framework. In this view, the true fabric of the cosmos is not the four-dimensional spacetime of Einstein's block universe, but a six-dimensional arena with two distinct time dimensions. Our familiar experience of past, present, and future, this relentless one-way flow, is not fundamental. Instead, it emerges from the complex geometry of this higher dimensional space, much like a two-dimensional shadow is cast by a three-dimensional object. We are not living along a line, but moving across a vast, timeless landscape, and our perception of a flowing moment is our particular path through it. Imagine you are a tiny ant crawling on the surface of a large, still pond. From your perspective, your world is two-dimensional. You can move forward, backward, left, and right, but the concept of depth is invisible to you. Now, suppose a leaf falls onto the pond, creating ripples that expand in perfect circles. As the ant, you would experience these ripples as a sequence of events, a before and after. The ripple reaches you, then passes. You perceive a clear arrow of time, but from a bird's eye view above the pond, the entire event is just a static, geometric pattern. The leaf's impact point, the expanding rings, they all exist at once in the larger, three-dimensional reality. The ant's arrow of time is not a fundamental law of the pond, but a consequence of its limited perspective and its particular journey across the surface. In the two-time framework, we are that ant. Our single, flowing time is the ripple we are crawling through. The true reality is the still, higher dimensional pond where all moments and all possibilities simply are. In this picture, the low-entropy beginning of our universe is not a mysterious starting point on a line. It is a specific boundary condition in this larger geometry. The reason we perceive an arrow, the reason entropy always increases, is because our conscious path through this timeless landscape is one that constantly moves from regions of simple geometry to regions of complex geometry. We are traversing a slope in the higher dimensional terrain, and that traversal feels to us like the passage of time. This framework is not just a philosophical curiosity, it is a serious, though highly speculative, attempt to resolve the deepest puzzles in physics. It offers a potential pathway to unify quantum mechanics and general relativity by providing a more fundamental arena where both sets of laws can coexist. It reinterprets the Big Bang not as a beginning of time, but as a particular feature in a timeless geometry, a cosmic shoreline we emerged from. While there is no experimental evidence for a second time dimension, the power of such ideas lies in their ability to shatter our assumptions. They force us to consider that our most basic experience of reality, the ticking of the clock in our chest, might be the most sophisticated illusion of all. A story written not by the laws of physics, but by the particular journey of our consciousness through a silent, eternal, and unimaginably vast cosmos. Our arrow of time might not be a universal rule, but a local ordinance. The cosmos could be far vaster and more varied than a single expanding universe, existing as a multiverse, an eternal, bubbling foam of realities. Within this infinite ensemble, the very laws of physics could differ from one pocket universe to the next. In some domains, the conditions might be so chaotic from the start that no clear arrow of time ever emerges. In others, the initial state could be configured so that their thermodynamic arrow points in what we would perceive as the reverse direction. In those realms, beings would experience cause and effect flowing backward, living their lives from what we call the end to what we call the beginning, yet to them, it would feel as normal and absolute as our own timeline feels to us. This grand perspective offers a powerful, if humbling, answer to the deep mystery of our own low-entropy beginning, the past hypothesis. We do not need to explain why our entire cosmos began in a special, ordered state. Instead, we simply find ourselves in one of the rare pocket universes where that specific, improbable condition happened to occur. In the infinite lottery of the multiverse, a cosmos with a strong, forward-pointing time arrow is a winning ticket. It is the only kind of universe that can produce stars, planets, and conscious observers capable of wondering about the nature of time itself. Our entire history, from the Big Bang to this very moment, is not the definitive story of reality, but simply our story, unfolding in our particular corner of an unimaginably vast and varied cosmic landscape. The universe seems to run like a colossal, predetermined machine, every event locked into a chain of cause and effect that began with the first moment. If every particle's path is set by unbreakable physical laws, then where does that leave our own choices? Are our decisions just illusions, the predictable outcomes of a cosmic script written at the dawn of time? This is the ancient conflict between determinism and free will, and our understanding of time's arrow brings it into sharp focus. In a completely deterministic block universe, your entire life story is already etched into the fabric of spacetime, a completed sculpture. From this perspective, the feeling of making a choice is like a reader discovering a plot twist, believing it was unexpected, even though the words were printed long ago. The initial low-entropy state of the Big Bang and the relentless laws of physics would have set every atom in your brain on its course, making your future as fixed and unchangeable as your past. Yet the quantum world introduces a tantalizing wild card into this seemingly rigid system. At the subatomic level, particles do not follow strict, predictable paths. They exist in clouds of probability, and their final state is not determined until the moment of measurement. This inherent indeterminacy means the future is not a single pre-recorded film, but a vast collection of potential scenes. Some physicists argue this quantum fuzziness percolates up to our scale, that the random decay of a single radioactive atom in your brain could, through a cascade of events, tip the scale between two nearly identical choices. In this view, the universe is not running a single, predetermined program, but is constantly branching into countless possibilities, and your conscious mind is the agent that navigates this probabilistic tree. So, is free will compatible with a universe governed by physical laws? Perhaps the answer lies not in defying physics, but in embracing our role within its framework. You are not an outside spectator to the cosmos, you are a physical process within it. Your brain is a magnificent, complex system that weighs options, simulates outcomes, and makes decisions based on a lifetime of accumulated memories, all of which are physical states shaped by the arrow of time. The choice you make feels free because it is the authentic output of your unique, intricate neural network, a system so complex that its actions are fundamentally unpredictable in practice, even if they are lawful in principle. Your will is not a magical force interrupting causality. It is causality itself, expressed through the magnificent complexity of your mind. The future may be written, but you are holding the pen, and every decision you make is a new sentence being inscribed upon the timeline of your life. So the great cosmic clock was wound at the moment of creation. Its relentless forward tick is the echo of a universe born in a state of exquisite order, a single, low-entropy configuration from which everything else had to follow. The second law of thermodynamics is the unbreakable rule that governs this journey, the reason we remember a past but can only anticipate a future. This arrow of time is not an abstract concept, it is woven into the very fabric of our reality, from the grand expansion of galaxies to the intimate firing of our own neurons. We are living inside this irreversible current, our every thought and memory a testament to the universe's one-way trip from order to disorder. The deepest questions still linger at the edge of our understanding, in the realms where quantum mechanics meets gravity and where consciousness meets the physical world. The mystery of time continues to challenge our finest minds, a puzzle that sits at the heart of both science and philosophy. If this exploration of cosmic origins has sparked your curiosity, please support the channel by liking this video and subscribing for more journeys to the edge of understanding. And we would love to hear from you. If you could reverse the flow of time for just a single day, what one moment would you choose to live again?